Hello friends and my dear students, I welcome you all to my channel. This video is part of the playlist NCERT Mathematics of class 9 uh, where I upload videos where I study the NCERT chapters sequentially and I it is just a walkthrough of the NCERT textbook. I explain the theory concept, explain the solved examples and also try to solve the exercise problems. In this video, I will continue the chapter 1 number systems. This is lecture 3. I've already completed lecture 1 and lecture 2. If you have not seen the previous two lectures, I highly recommend that you please watch them so that you will have the continuity uh, of this chapter. So in this lecture 3, I will discuss the section 1.3 from the from the NCERT textbook, which is about decimal expansion of real numbers. Real numbers means rational and irrational numbers. So let's get started with this video. Okay, so I have the PDF version of the NCERT textbook on the left hand side, and on the right hand side, I will explain and note down all the important concepts, formulas, and will solve the exercise problems. Just to give you a recap, what we have done in the previous lecture 2, uh, let me scroll back to the lecture 2. Uh, so this was lecture 2. We discussed briefly about the natural numbers, the whole numbers, the integers, and the rational numbers. And we saw, we studied the irrational numbers, that any number that cannot be written in the form p by q, where p and q are integers and q not equals to 0, is an irrational numbers. We saw that there are infinite number of irrational numbers on the number line. We saw some examples of irrational numbers, and so we studied that the collection of rational and irrational numbers makes is called the real numbers, and that the number line is called the real number line because in this number line we only have rational and irrational numbers. And we saw how to locate a irrational number on the number line. We saw how to locate square root of 3, square root of 2, and then square root of 5 on the number line, and square root of 6, also square root of 10. And we solved the exercise problems of exercise 1.2. If you have not seen this video, I highly recommend that you please watch this video. Okay, so in this lecture 3, we will study on the how do we find the decimal expansions of real numbers. Real numbers means a rational number and irrational number. So it says that we are going to study rational and irrational numbers from a different point of view. We will look at the decimal expansions of real numbers and see if we can use the expansions to distinguish between rationals and irrationals. It says, I will just jot down the important points. You can also note them down in your notebook. Uh, we says that decimal expansion, we use decimal expansions to distinguish uh, between rational and irrational numbers. So irrational numbers are denoted by the letter q dash, while rational numbers are denoted by the letter q. So the decimal expansion will be primarily used to distinguish whether that number is rational or irrational. Okay. Uh, so we will see with an example. First, we will see how do we find the decimal expansion of rational numbers. Uh, so example uh, of decimal expansions of 10 by 3, 7 by 8, and 1 by 7. So let's do the decimal expansion. You have already learned this in your previous classes. So let's see what is uh, uh, using the long division method. Let's divide 10 by 3 and find the decimal expansion. So we have 3, over here we have 9, 1, then we have a decimal point, again 10, again 3, again 9, 1, 10, 3, this way. So we can see that the long division method is not ending. We are keep on getting the same remainder. I will mark the remainder. I will mark the remainders for easy to understand and explain the concept. So the first remainder was 1. Again, the second remainder was 1. The third remainder was 1. The fourth remainder was, and we will keep on having this 1 as remainder. It will never end. And okay, so now let's see what happens if you divide 7 by 8. Uh, so we will have 0, we will have 8, 64, this is 6, we will have 0, then we will have 7, 56, we have 4, 0, then we have not 40, yes, 40, and we have 5. So here the long division method has come to an end. The remainder was 6, 4, and 0. What about if you divide the 1 by 7? So let's see, 0.1 is 7. We got remainder 3, then 4, 28, we got remainder 2, then 0, then 2, we have 14, remainder 6, 0, then we have 8, 56, we have 4, 0, we have 5, 35, we have remainder 5, 0, we have 7, 49, 1, 0. Okay. Then we have uh, so we have again come to the point 10. So initially we, okay, let's do it. Then we will have 1, uh, 7, then 3. So as you can see, 3 has again come up. The first remainder was 3. Let's mark the remainders. 3. Then we got 2. Then we got 6. Then we got 4. Then we got 5. Then we got 1. And 3 started repeating. The first remainder was 3, then it was 2, 6, 4, 5, 1, then 3. Again it started with 3. So from after 3 it will be 2. So this is the decimal expansion. Now, uh, so we see that for this, when we divide 10 by 3, we got remainders. We got remainders 1, 1, 1, 1, 1, and so on. As you can see, the long division method will never end when we divide 10 by 3. Also here, this will go on. 3 dot means it will never end. It is not an, it will never end. The 3, the digit 3 after decimal point will never end. It will be infinite number of digit 3 after the decimal point. So, and the divisor was 3 over here. Uh, Remainders for this, the long division method came to an end with a and the final the remainder was 0. So remainders were 6, uh, 4, 0, and divisor was 8. And for this remainders was, the first remainder was 3, 2, 6, 3, 2, 6, 4, 5, 1, 3 again, and like this. After 3 it will again be 2, 6, uh, 4, 5, 1, and it will continue, it will never end. So the remainders will never end. So we will have remainders 3, 2, 4, 5, 1, 3, 3, 2, 6, 4, 5, 1. Again it will repeat the same remainders 3, 2, 6, 5, 3, 3, 2, 6, 4, 5, 1. Again it will repeat the same sequence of remainders. So when we write dot 3 dot, we mean that these remainders is never ending. Now the book says what we have noticed. The book says that we have noticed while doing the decimal expansion, we have noticed three things, that either, so these are all rational numbers. The examples we have taken are rational numbers. Uh, these three are rational numbers. So three things we noticed, that the remainder is either becoming 0 after a finite after a finite step of doing long division method. The remainder is becoming 0. In this case, for when we divide 7 by 8, when we do 7 by 8, the remainder is becoming 0 after a finite step, or the long division method is never ending, and we see that, okay, so it's better we write it down. uh, Things to notice are one remainders either become zero, remainders either become zero after some finite steps of division of division or start or starts repeating themselves. For the first case, when we divide 10 by 3, we see the remainder, we are only having one remainder and which is repeating. The remainder is 1. So 1 is repeating all the time. In the second case, the remainder is ultimately becoming 0 after a finite step of division. And in the third case, third example, also the remainder, the long division method is not ending, and we see repeating, the remainders repeat. So the remainders in the third case, 3, 2, 6, 4, 5, 1, this repeats again and again. So that is, we notice here. Also, what do we notice? The number of entries in the repeating string of remainders. By repeating string of remainders, it means, so over for the first one, the remainders are 1, 1, 1, 1, 1, 1. So here the repeating string of remainder is 1. For the third case, the remainders are 3, 2, 6, 4, 5, 1. Again, it starts from 3, 2, 6, 4, 5, 1. So here the repeating string of remainders is 3, 2, 6, 4, 3, 2, 6, 4, 5, 1. This is the repeating string of uh, remainders. So it says that number of entries. Number of entries means the number of digits in the repeating string of integers, in the repeating string of remainders. Number of entries in the repeating string of remainders is less than the divisor. Is less than the divisor. It means for the first one, the number of remainders, the number of digits in the repeating string of remainders is 1. The number of entries is 1 because the repeating string in the first case is the repeating string of integers for the first case is 1. So we have 1 digit. So 1 is less than 3. In the third case, the number of entries in the repeating string of integers is 3, 2, 6. The repeating string of integers is 3, 2, 6, 4, 1. 3, 2, 6, 4, 5, 1. So how many digits are there? 6. 1, 2, 3, 4, 5, 6. And 6 is less than 6 is less than divisor 7. So that is what the point number 2 says. Number of entries in the repeating string of remainders is less than the divisor. So I hope you understand. I hope you understood the concept of repeating string of remainders. I will once again explain. The repeating string of remainders is all those the collection of remainders which is repeating. In the first case, we see that the remainders 1 is repeating again and again 1, 1, 1, 1. So here the repeating string of remainders is 1. So the number of digits, the number of entries in the repeating string of remainders is 1. For the third case, the repeating string of remainders is 3, 2, 6, 4, 5, 1. So how many entries are there? There are 6 entries. Okay. Now the third point to notice here, it says if the remainders repeat when there is when the long division method doesn't end, we never get a remainder 0, and the remainders are repeating, then we get a repeating block of digits in the quotient also. Okay, so this is very important. If the remainders repeat, if 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 the remainders repeat, then we get a repeating block of digits in the in the quotient. Now, repeating block of digits. This is essentially the same concept like repeating string of remainders. So, for the first case, you see in the quotient, the digit 3 is repeating. So, after the decimal point, we are having 3, 3, 3, 3, 3, and it will never end. So, for the first case, the repeating block of digits is 3 because 3 is repeating. 3 is repeating. So 3 is the repeating block of digits in the quotient for the first case. For the second case, we are not having any repeating digits because we are the long division method is ending after the final step, and we are having the remainder 0. For the third case, you see the digits after the decimal point in the question is 142,857. Again, one has come up. So after 1, it will again be 4, 2, 8, 5, 7, so on. So the repeating string of digits in the quotient is 142,857. Okay. For the third case, the repeating string of digits in the quotient, the repeating block of digits in the quotient is 142,857. So when the remainders repeat, then in the quotient we get a repeating block of digits. Okay, I will just to have better clarity for repeating block of digits in our example for 10 by 3 it is 1. So the repeating block of digits is 1. For the last one, that is 1 by 7, it is 1 by 7, it is 142,857. 142,857. This is the repeating for 10 by 3, the repeating block of digits in the quotient after the decimal point is this. And for 1 by 7, the repeating block of digits in the quotient after the decimal point is this. So when we find decimal expansion of rational numbers, we find these 3 important points. Either the division is ending after finite steps with the final remainder being 0, or the remainder doesn't end and we get a repeating string of remainders, and we also get a repeating block of digits in the quotient. Okay, so let's proceed with the textbook. It says that although we have noticed this pattern using only the examples above, it is true for all rationals of the form P by Q. So on division of p by q, two main things happen. So when we divide, when we do a division p by q, where p is an integer, q is also an integer, and q not equals to 0, two things can happen. Two things can happen. That is, either the remainder becomes 0 or never becomes 0, and we get a repeating string of remainders. So the next thing is, uh, uh, if we divide p by q, where p and q are integers and q not equals to 0, then two things can happen. If you divide p by q, where p and q are integers and q not equals to 0, two things can happen. The first one is, case 1, in the book it has shown using case. So case 1, the remainder becomes 0. The remainder becomes 0, obviously, after some finite number of steps, meaning after doing some, like in this example for 7 by 8, after 1, 2, 3, after 3 steps, we got the remainder 0. So either we will get the remainder becomes 0. In this case, it says in the, in the example of 7 by 8, we found that the remainder becomes 0 after some steps, and the decimal expansion of 7 by 8 is 0.875. Other examples are half is 0.5, or 639 by 250 is 2.556. In all these cases, the decimal expansion terminates or ends after a finite number of steps. We call the decimal expansion of such numbers terminating. So when the remainder becomes 0, this means that uh, the decimal expansion terminates after a finite number of steps, and the decimal expansion terminates after a finite number of steps. So the final remainder becomes 0, and this type of this kind of decimal expansion is known as terminating, or such rational numbers, that is p by q, we are trying to divide. So we are trying to divide p by q. So p by q is a rational number. So if the decimal expansion terminates after a finite number of steps, we say that the rational number p by q is terminating, or the decimal expansion of such numbers, the remainder becomes 0. Okay, so we say the decimal expansion of p by q is terminating. Okay, this is an important term, terminating. The decimal expansion of p by q is the rational number, is terminating, meaning uh, the long division method, method, when we divide p by q, comes to an end after a finite number of steps, with the final remainder being 0. Okay, this is the case number 1 when the remainder becomes 0 after a finite number of steps. We get, in such case, the decimal expansion is called terminating. This case 2, is the remainder never becomes 0. Case 2 is the remainder never becomes 0. So, what does it mean? The remainder never becomes 0. Uh, in this case, we see that the remainders repeat after a certain stage, forcing the decimal expansion to go on forever. In this case, the decimal expansion never ends and the remainders repeat themselves. And also we have seen, we also see repeating block of digits in the quotient. So, uh, decimal expansion never ends. Also, what do we see? Remainders repeat themselves. Uh, there is repeating remainders after after a certain stage, means after a certain number of steps the remainder starts repeating. And also we see that uh, also uh, we have a repeating block of digits in the quotient. We have repeating block of digits in the quotient. So in this case we say that the decimal expansion is non-terminating. So we say the decimal expansion is non-terminating and non-terminating recurring or repeating. Recurring means repeating. We can see that we see that we are having repeating block of digits in the quotient, and the process of decimal expansion is never ending because we are seeing that the remainders also repeat and they never end. We never get a remainder of 0. That is why this kind of decimal expansion is known as non-terminating recurring. So we say that the rational number p by q in this case has a non-terminating, recurring or repeating decimal decimal expansion. So that is all for this. Thus we see that the decimal expansion of rational numbers have only two choices. Either they are terminating or terminating. Okay, now suppose on the other hand, on your walk on the number line, you come across a number like 3.142678 whose decimal expansion is terminating, or a number like 1.272727, that is okay, one more thing. When so we saw that there is a notation that we need to understand. We saw that when we divide 10, when we divided 10 by 3, we are getting the quotient as 3 point. It is like the quotient is 3.333, and this 3 will keep on repeating, it will never end. So to to tell that it never ends, the digit 3 never ends in the question, we put 3 dots, means the digit 3 will keep on repeating, it will never end. And this thing is written in a short form or in another notation as 3.3 bar. What is this? We just keep the digits in the question which is repeating, and we put a bar on top of the digit. Now for this case, we have only one digit that is repeating, which is 3. So the repeating block of digits here in the question is 3. So we put a bar on top of 3. On the other hand, for 1 by 7, we saw the decimal expansion was 0.14287, and again it will start. This was the repeating block of digits, and it will repeat again. So we will have 1 again, 142,857. So this way it will keep on repeating. By 3 dots, we say that these digits never end. The digits in the decimal after decimal point is never ending. Now, this thing, for this example, in the shortened form, will be written as 0 point. We write the repeating string of digits in the question. The repeating string of digits, that the repeating block of digits, the repeating block of digits, which is 1, 4, 2, 8, 5, 7. This is the repeating block of digits, which repeats again and again. So we put a bar above all the digits. Okay. So this is the way we denote a non-terminating recurring decimal expansion. So okay. Now it says that if you are working on the number line, and if you come across a number like 3.142678 whose decimal expansion is terminating, or a number like 1.27 bar, means the decimal expansion is non-terminating recurring, can you conclude that it is a rational number? Can you conclude that it is a rational number? What is trying, okay, so what it is trying to say or ask is that if you are given in a number line in the real number line, if you get in the real number line, if you get a number, say a number, say a number R1, which is say we get a number R1 like 3.1268, and another number say R2 which is like 1.27 bar. So the R1 is a is a terminating decimal rational number, is a number having a terminating decimal expansion, and R2 is a number, it is a number. We are not saying whether it's a rational or irrational, we are saying that it is a number, and R2 is 1.27 bar, which means it has a non-terminating recurring decimal. Now, if you are given these two numbers, the question is, can you, in the real number, if you get a number, can you say that the numbers R1 and R2 are rational that is the question is, can you write R1 and R2 in the rational form P by Q, where P and Q are integers and Q not equals to 0. This is the question. If you are given two numbers where one number has the decimal expansion which is terminating, and another number which has the decimal expansion non-terminating recurring, from these given two numbers, can you say that they are rational? Meaning, can you rewrite these numbers in the rational form P by Q, where P and Q will be some integers and Q not equals to 0? Answer is yes, we can. So essentially, the point is, given a number which has a decimal expansion, which has a terminating decimal expansion, or a number which has a non-terminating recurring expansion, we can always convert them into rational form P by Q. That is what we will study next. So it says that we will not prove it but illustrate this fact with a few examples. So the terminating cases are easy. So this point, the last point which I have stated as a star, in the book it has explained through examples. So let's see what are the examples. What does the example say? Show that is the rational number. Show that 3.142678 is a rational number. Now this is easy because we know the decimal expansion is terminating. We have some fixed number of digits after the, in the question, after the in this number we have fixed number of digits after the decimal point, which are 142678. So we can always write this as, so how many digits are after the decimal point? 3 digits, 6 digits. So we can always say, write these as divided by we can always say this. So we can always divide, we can always write this kind of decimal number this kind of number where the decimal expansion has fixed number of digits by dividing by 10 to the power something, where basically how do we convert this kind of numbers with fixed number of digits in the decimal after decimal point into a rational number like p by q form. So the idea is, let's say the number was uh, uh, so the idea is, we see how many digits are there after the decimal point. In this case there are 6 digits. So actually this will be 10 to the power 6. The whole number, we ignore the decimal point, the the number we get by ignoring the decimal point, that divided by 10 to the power 6. Why 6? Because after the decimal point we are having 6 digits. So we can always do this for a number which has terminating decimal. Now example 7, show that the number is a rational number, which also means we have to show that this number 0.3 bar can be written in the form p by q. So what is the steps? What is the okay, for so essentially what we are trying to do is we are trying to write a given number which has a non-terminating recurring decimal in the form p by q. So the steps is, the first one where we have terminating decimal, it is easy. As I already said, you ignore the decimal point, you take the whole number without knowing the decimal point, write it down and divide it by 10 to the power. The power will be the number of digits in the number after the decimal point. Now for this, steps are, first you write the number as it is. Let's say we call the given number as x. So we write x equals 0. We write that x equals 0.333, and definitely it will never end. The digit 3 will be repeating. So we also say we give the dots. Now what we do is, so we see that the repeating digit, the repeating block of digits, in this number is 3, because 3 is repeating. 3 is repeating, right? We have 3 bar. So the repeating block of digits is 3. So how many digits are there in the repeating block of digits? 1, only 3. So 1. So we multiply. In the second step, what we do is we multiply this equation 1 with 10. Why 10? Because there is only one digit in the repeating block of digits in the in the number. If there was two digits in the repeating block of digits, we would have multiplied with 100. So 10x, since we have only one digit in the repeating block of digits, we are multiplying with 10x equals to, when we multiply 10, this becomes 3.3333. This will repeat. We are getting this. Now what we will do is we will subtract equation 1 from equation 2. If we subtract, if we uh, uh, this, okay, in the step 2 we got 10x equals to 3.333. Now 3.333 can also be written as 3 plus 0.333. Now this 0.333 is the same number that we were given, it is x, so we can write it as 3 plus x. So we got an equation that 10x equals to 3 plus x. From here we can say that 9x equals to 3 or x equals to 3 by 9, which is 1 by 3. So we got a rational form 1 by 3. Once again, let me explain you what we just did. We are given a number which has a non-terminating recurring decimal, which is 0.3 bar. So the repeating block of digits in the number is 3. And how many digits are there? 1. So we first write down x equals to the given number, and then we multiply the first equation with 10. Why 10? Because there is only one digit in the repeating block of digits in the given number. So 10x equals to 10 into 0.333, which becomes 3.333, and which can be rewritten as 3 plus 0.333, and 0.333 is the original number given, so we can replace that by x. So we get the equation 9x equals to 3, so we got x equals to 3 by 9 or 1 by 3. Now let's see example 8. Example 8 show that one point, this is also a non-terminating recurring decimal number. I mean a number which has a non-terminating recurring decimal expansion. So 2727 is repeating again and again. So we can write it as 1.27 bar. So 27 is the repeating block of digits. Okay. So repeating block of digits. So steps. Number 1, we write x equals to the given number. So 1 point, we write 27. We write a couple of 27. 3 times will be fine. So the repeating block of digits is 27. So we write down 27 3 times. Of course, we must at the end write dot dot dot. Only then it will mean that it's a non-terminating decimal and 27 is repeating again and again. So now here's, in this case, we see the repeating block of digits is 27, and we have 2 digits. 2 digits in the repeating block of digits, 2 digits. So in this time we will multiply equation 1 with 100. 100 equals to 100 into 1.272727 dot dot dot. This becomes 127, and then we are having the same 2727 will repeat. This we can write it as 1 so the given number, original given number was 1.272727, and we got 100x as 127 point this. We can write this as 126 plus 1.272727 like this. Now this becomes 1.272727 is the original given number x. So we got an equation from here. If we solve, we see that 99x equals to 126. Therefore, x equals to 126 by 99, which if you simplify further will be 14 by 11. So, okay, so we uh, we saw with two examples how we can convert a given number with a non with a non-terminating recurring decimal expansion to a rational number in the form p by q. In the first case, example 7, uh, the repeating digit of block was 3, and so we wrote x equals to the given number, and then in the second step we multiplied x, the first equation, with 10. Why 10? Because there was only one digit in the repeating block of digits in the given number. So we got 10x equals to 3.333, which we rewrote as 3 plus 0.333, which is 3 plus x, and we got x equals to 1 by 3. In example 8, we see that the repeating digit of block has two digits. So we multiplied here with 100. So the steps are same like before. Just in this case, we multiplied by 100, and we saw that 100x equals to 127.272727. So the idea is, on the right hand side, we want to have x again. So from 127.2727, we the trick we this is a so we rewrote as 126 plus 1.272727, so that we can have x on the right hand side. So we got 126 plus x. Now we solved the equation 100x equals to 126 plus x. From that equation we got x equals to 126 by 99, or which is 14 by 11. Now let's see example 9. So that okay, so that is actually the question is, so that is a rational number. That was the actual question. So that 0.2353535, that is the is a rational number. In this example, you see that the bar is on top of 3 and 5 only. So the repeating block of digits in this number is 35, 35. So there are again two digits in the repeating string, in the repeating block of digits. So the steps: 1, we write x equals to the given number, that is 0.23535 is repeating. We write 35 three times is fine, and then we write the dot. Then, since there are two digits in the repeating block of digits, the repeating block of digits is 35. So 35 contains two digits. So we multiply the equation 1 with 100, and it becomes 23.5353. hmm. No. So in the decimal part, in this example, we see that the decimal part has one digit which is not repeating, which is 2. We have in the decimal part one digit which is 2 that is not repeating. After 2, we have repeating digit, repeating block of digits which is 35. Since there are two digits in the repeating block of repeating block of digits, we multiply with 100. So 100x becomes becomes 23. This uh, so somehow we have to bring x again on the right hand side of the equation. X is 0.2353. Uh, so from 23.53535, how we can rewrite this number? So it will have um, how we can break this number 23.5353 so that it will have one part x and another part some decimal number, some other number. So um, 23. Okay, so we see we can rewrite this as we have 53535, but after the decimal, uh, in the original number, after the decimal point, we have 2353535. So we have to break this number in such a way that if you do 23.3, then we can say we can have 2, 3, 5, 3, 5. There will be dot over here. We are getting this. So I've extracted 23.3 from the number 23.5353. This number I have taken out 23.3. So that will leave the remaining number as 0.2352353535. So this thing is x. This thing is x. It's better if you so this thing is x, and also this thing is x. So we have to somehow break this number into a form into two numbers where one number will be x again. So that is the idea. So now we get this. So this implies that if we bring the so this is 23.3 plus x. This implies 99x equals to, now this is 23.3. This is fine because 23.3 can be easily written as 233 by 10. So this we can easily write it as in the rational form as this. So therefore x becomes 233 by 10 into 99, which is 233 by 990. So we converted the given number into a rational form. Okay, so it says in the textbook every number with a non-terminating recurring decimal expansion can be expressed in the form p by q, where p and q are integers and q not equals to 0. So in summary, as a result, what what results we got? So uh, what results we can say is that number one, the we see that the decimal expansion of a rational number is either terminating, like the division process will end after a certain final steps, leaving remainder 0. So in that case, we see the decimal expansion is terminating, or non-terminating, means it will not terminate, or non-terminating recurring, also known as repeating. Instead of recurring, the word recurring and repeating are same. We sometimes say non-terminating recurring, or we sometimes say non-terminating repeating. So this is one result we got. The other result is the reverse of this. I mean, if you are given a rational number and if you find its decimal expansion, you will see that the decimal expansion is either terminating or non-terminating recurring. On the other hand, a number whose decimal expansion is terminating or non-terminating recurring, a number whose decimal expansion is terminating or non-terminating recurring is rational. So if you are given a number where you see the decimal expansion is terminating or it is non-terminating recurring, you can say that it is a rational number, and that is, it can be written in the form p by q. That is the number point 2. Point 1 says if you are given a rational number, that is a number in the form p by q, you will say that the decimal expansion will be either terminating or non-terminating recurring. Okay. So now it says, so we have understood, we have studied the decimal expansion of rational numbers. Now, what about the decimal expansion of irrational numbers? It says that we know that the real numbers are formed of only rational and irrational numbers. On the real number, on the number line, any number will either be a rational number or an irrational number. And if a number is rational, then its decimal expansion will either be terminating or non-terminating recurring. So from this we can guess, or we can easily conclude, that if a number is irrational, then definitely its decimal expansion will not be terminating, because in that case it would have been rational. So the only option about the decimal expansion of an irrational number is that it will be non-terminating and non-recurring. So the decimal expansion will never end, and also we will not get any repeating block of digits in the question. We will not see any repeating block of digits after the decimal point. So this is how we conclude about the decimal expansion of a irrational number. So let me quickly results. Okay, now these two are results for rational number. Okay, so results for rational, these results Now, results for irrational number is that we know uh, any given number, any given real number, any given real number is either rational or irrational. Any given real number is either rational or irrational. If uh, all rational numbers, all rational numbers, all rational numbers will have decimal expansion either terminating or non-terminating recurring or repeating. So, all rational numbers will have decimal expansion either terminating or non-terminating recurring. So, an irrational number uh, will have decimal expansion will have uh, decimal expansion non-terminating and non-recurring. So, this is important. Now, why we concluded that an irrational number will have a decimal expansion non-terminating and non-recurring? Because the decimal expansion of a rational number of an irrational number cannot be terminating, because we have already seen that only a the rational number decimal expansion is terminating. All rational number decimal expansion is either terminating or non-terminating recurring. So if a decimal expansion has a terminating decimal expansion, it has to be rational number. Now, if a given decimal expansion is non-terminating, in that case, we again have two choice. It could be either recurring or non-recurring, meaning the decimal expansion will have either uh, a repeating block of digits, or it may not have a repeating block of digits. For rational numbers, we have seen that uh, if it has repeating block of digits, it has to be a rational number, because we have already seen that every rational number has either terminating decimal expansion or non-terminating recurring expansion. So the only choice of the decimal expansion of an irrational number is it has to be non-terminating and non-recurring. That is the result. So please remember this. Now let's see what's there in the textbook. So it says that recall. So any rational number will have a decimal expansion where the digits will have it will never end. There will be infinite number of digits after the decimal point, and there will be no repeating pattern. So uh, uh, example rational rational numbers like s equals to 0.1010, some non-ending infinite number of digits which has no pattern. Okay, no pattern. Or we have seen that square root of 2 is a irrational number, and it has been found out, this has been found that square root 2 is 1.41421356 and so on. It has many more digits, but endless digits, but there is no pattern, there is no repeating block of digits in the after the decimal point. Also note that uh, 22 by 7, this is a rational number, is often taken as an as an approximate value of pi. So in the previous lecture we have seen that pi is a irrational number. Basically what pi is the ratio between the circumference and the diameter of any circle. You take any circle of any of any radius, if you divide its circumference by the diameter, that is the, if you measure the circumference and you measure the diameters and take the ratio, that value is denoted as pi. And so pi, the actual decimal value of pi, which is actually 3.141559263 and so on. It has more digits, many more digits, infinite number of digits, but there is no repeating block of digits. Often in the, for the sake of calculation, we consider 22 by 7 as an approximate value of pi, but uh, but uh, but note that 22 by 7 is not exactly equals to pi. 22 by 7 is an approximate value of pi. Just keep this in mind. Okay, what else is there? Let us see how to obtain irrational numbers. Okay, so the next topic is how we can find irrational numbers between two given rational number. So the next topic is uh, finding irrational number uh, finding irrational numbers. Finding, how do we find irrational numbers? So example 10 says find an irrational number between 1 and 7 and 2 by 7. So in the beginning we found 1 by 7, the decimal expansion we saw 1 by 7. What was 1 by 7? 1 by 7 was yeah, 1 by 7 was 0.142857 1. So the repeating digit of blocks in the question of 1 by 7 was 142857. So from here we know that 1 by 7 is 0.142855. This is the repeating digit of blocks, so it will repeat. So we put a bar on top of that. Now it is asking to find the rational, and now so 1 by 7 is this. So what will be 2 by 7? So it is basically twice of 1 by 7. So we can write this 2 into 1 by 7. This is 2 into 0.142857 bar. Now you can simply do the multiplication and see that it will be, if you multiply this 0.142857 by with 2, it will be 14, 11, 17, for a 5, 8, 2. And also notice that this will be bar, this will be the repeating block of digits. This will be the repeating block of digits of the number 2 by 7. Now, so we know that we found that 1 by 7 is this and 2 by 7 is this. Now to to find an irrational number between 1 by 7 and 2 by 7, what we do is we take any number that will lie between these two, but there will be no repetition of digits, and it will be have infinite number of digits. So we answer, then we find a number between this and so we just have to find a number between this and this that will have non-terminating non-recurring that will have non-terminating and non-recurring decimal expansion. And obviously we can have many such numbers. I mean, arbitrarily choosing digits without any, that will have no repetition, but that will lie between these two numbers. There are many. So just for an example, such a number can be, so we have to choose a number between 0.142857 and, of course, over there is a bar, it's a repeating, and 0.285714. So let's say we can have, it must be, we can have, say, so 1, 4, and over here we can have 3. Anything you can say 1, 5 also, that will also do. So 143, and randomly you take any number of digits 0, 1, 1 that has no that has no repetition whatsoever, like this. This is a example number that lies between the rational numbers 1 by 7 and 2 by 7. The important thing is that 1 by 7 we already calculated earlier, it is this. So 2 by 7 is 2 into 1 by 7, and 1 by 7 we know. So we just do a simple multiplication, and the but over for 285714 it will be a bar. Over here, I would like to point out something that you maybe you are not convinced that 2 by 7 will be 0.285714 whole bar. But this is the case. Let's try to see what will be. So, if we using this concept, 3 by 7 will be 3 into 1 by 7, which is 3 into, and we already know 1 by 7 is 1, 4, 2, 8, 5, 7 bar. So this becomes, if you do a simple multiplication, this will be 7, 3, 21, 15, 17, 24, 25, 6, 8, 12, 4. This will be this. So we just multiplied, ignore the bar, we just multiplied 0.142857 with 3, and this was the result, and we put the bar after the decimal point. Similarly, you can check yourself indeed if this is the answer by actually doing the long division of 3 by 7, and also check for 2 by 7. So I will just show another, let's say 6 by 7. 6 by 7 will be 6 into 1 by 7 equals to 6 into 0.14285 whole bar. This is equals to 6, 7, 42, 4, 30, 34, 48, 51, 12, so 17, 24, 25, and 8. You can check it out. I just did a simple multiplication ignoring the bar with 6 and 0.142857, and I put the bar on the 6 digits. So, okay, you can also verify by actually doing the long division of 6 by 7 that indeed you are getting the result as this. I just leave this as an exercise for you. Please check it out. Then only you will be convinced. Now, let's do the exercise problems. The one says, write the following in the decimal form and say what kind of decimal expansion each has. So we are given some rational numbers. These are all rational numbers. We have to find the decimal expansion, and from the decimal expansion we have to say whether it is terminating or it is non-terminating recurring. So the first one is 36 by 100. It is simple, very simple. We know that this will be 36. So we have terminating. I'm not writing terminating decimal expansion. It's understood. It is asking what kind of decimal expansion it has. So I'm just writing what kind of decimal expansion it has. It has terminating. Now 2 is 1 by 11. 2 is 1 by 11. So it's better we do the long division method and find it out. So 11 divided by, we see 0 point mm, 0 9 9. We have 9 99, then we have 1 and 1, we have again 0 0 0 9 99 1. So this keeps on repeating. As you can see, again we will have this and this 99. So the remainders, the every time we are having 10 as the remainder, 1 as the remainder, it is repeating. So the in the question the repeating block of digits is 09. The repeating block of digits is 09. Uh, so we can write this as 0.0909009 and so on. This is 0.09 bar. First I will solve all the problems, then I will check the answer with the answer key that is given in the NCERT textbook. So I hope I am right. So this is what I am getting. Okay, so 3 is 4 1 by 8. This is actually, this is a mixed fraction. If we convert it to a proper fraction, we get 33 by 8. Now let's do the long division and see 8 4 32. The one has remainder 10.182 to 16 4 0 5 40 0. So it is a terminating. So obviously terminating, this one will be non-terminating recurring. Number 2 is the rational number in for number 2 is non-terminating recurring, and the third one, we are the division process is ending, terminating after finite steps. We are having remainder 0. So 33 by 8 is 4.125 terminating. The decimal expansion is obviously terminating. Let's see 4. 4 is 3 by 13. Let's do the long division. 0.226 4 0 3 39 1 0 it is for 3, right? Okay, so 0 point 226 4 4 0 3 39 1 0. So 0 0, then this will be 8, that is 94. No, sorry, will be 7 91 9 0 91 90, we will have 6 6 72 72, we have 18, no, what I'm doing, 78 78, we have 12, we have 12. Okay, so mm, 12, 0, 9, 117. Since 3 by 13 is a rational number, the decimal expansion should either be terminating or non-terminating recurring. So as of now, it is not repeating. Okay, let's do some more steps. This is 3, and okay, I think now it will start repeat because we again got 3, and initially we started with 3. So 3, and we will have 3 0, again we have 2. So now it is repeating. Now it has started to repeat. See, now it has started to repeat. So again we will have 3 39 1 0 0, we will have 0 7, and so on and so on, 9. So we can see 3 by 13 equals to 0.23076902307. Just start repeating. So this will basically be 2307690. So this is non-terminating recurring. This was 4. Let's see what is 5. 5 is given 2 by 11. You have to do the long division method. So 11 divided by 2, we have 1. We have 1 9 0. By the way, if did I do the long division method correctly? Okay, I will check once I complete all the questions. So uh, 8 88 2, and it start repeating again. So we will have 1 again, and we will have 1 1, we will have 9 0, again we will have 8 88, and 2, and so on. So 2 by 11 is 0.8118, so on. This is 0.18 bar. So it is non-terminating recurring. Okay. What about 6 329 divided by 400? We can uh, mm, we can write it as 3 in the long division method by 100. So we can first compute 329 by 4, and whatever decimal expansion we are getting, we can that finally divide that by 100. uh, can we do that? Yes, let's see. So 4 329 is 8 320 0 9. So 2 8 1 0 point 2 8 0 4 16 4. No, sorry. uh, 2 and then 5. So this is a, so this becomes that 3 to 9 by 400 will be 8 to, since this is a terminating decimal, definitely by 100 is 0.8225. So it is a terminating decimal expansion. The decimal expansion is of type terminating. Okay. What does 2 says? You know that 1 by 7 is this thing. Can you predict what the decimal expansion of 2 by 7, 3 by 7, 4 by 7, 5 are without actually doing the long division? If so, how? Yes. So we know that 1 by 7 equals to 0.414285 bar. So 2 by 7 will be 2 multiplied by 1 by 7. This is 2 multiplied by we simply do the multiplication, and remember that since 1 by 7 is having uh, 6 digits in the repeating block of digits, so 2 by 7 will also have 6 digits in the repeating block of digits. So we just multiply this thing and we get 14, uh, 14, 11, 17, 5, 8, 2, this, and 3 by 7 is 3 into 1 by 7, which is 3 into 0.142857. This is 0. If you multiply 0.142857 by 3, we get 21, 15, 17, 24, 25, 6, 8, 12, 4. This 4 by 7 is 4 into 1 by 7 is this is 0 point, we simply multiply 0.142857 with 4, we get 28, 20, 22, 32, 34, 48, 11, 16, 17, 5. So 5 by 7 will be 5 into 1 by 7. Uh, this is 0 0.35, 35, 25, 28, 32, 13, 21, 7. One thing you might one thing you might have noticed that uh, when we have non-terminating recurring decimal expansion, the number of digits the number of digits occurring in the repeating block of digits will always be less than the divisor, that is less than 7. Over here uh, the the number of digits in the repeating block of digits is 6, so it is less than 7. And also notice that the digits that are occurring in the repeating block of digits, which are 1, 4, 2, 8, 5, 7, that will those digits will only occur in the other decimal expansion, like in the decimal expansion of 2 by 7, 3 by 7, 4 by 7, 5 by 7. You see the um, you see the digits in the repeating block of digits, they are same. No, we have 3 here. Yeah. Okay, so ignore that. So always remember that the number of digits in the repeating block of digits in a non-terminating recurring decimal expansion will always be less than the divisor. Okay, so the final one, 6 by 7 is 6 into 1 by 7. This is 6 into 0 0.142857. If we just do the multiplication, we get 42, 34, 48, 51, 12, 17, 24, 25, and 8. So this. Okay, let's number 3 says express the following in the form p by q, where p and q integers. So we are given some non-terminating recurring decimal numbers which have non-terminating recurring decimal expansion. We have to convert them into the rational form p by q. So as you might remember, the steps that we took while converting a decimal number having decimal expansion, non-terminating recurring decimal expansion, to form p by q, these were the steps we took. So for the first example, for the first one, it's given x equals to 0.6 bar. So we have one digit in the repeating block of digits, which is 6. So since there is only one digit, we multiply x by 10 and we get So this is basically 0.6666 dot dot dot. We multiply 10x, we get 6.6666 dot dot dot. So we subtract the two equation and we get that 10x, okay, this is equals to 6 plus 0.666 dot dot dot. This is 6 plus this is x. This implies 9x equals to 6. Therefore, x equals to 6 by 9 equals to 2 by 3. The second one is x equals to 0.4. The bar is on 7. So the repeating block of digits is 7 and it's only one digit 7. So again we multiply it by 10 and we get 10x equals to, so this is basically 0.4777 like this. We get, when we multiply with 10, 4.7777 dot dot dot. Now somehow from 4.777 we have to split into two terms where one term will be x. How can we do that? So what we do is, we have the after decimal after decimal point we have 4, then 7 is repeating. Over here we have 7 is repeating. So we have to extract 4.3 and then we will get 0.4777. I hope you understand this point. This is a very this is the tricky point. This is a tricky step. So from 4.777 we have to somehow split it into two terms so that one term will be x. So from 4.777, how do we split it to get x? X is 0.4 and then 7 repeats. So that's the reason I took out 4.3. So if you took out 4.3 from 4.777, you will get 0.4 and then 7 repeats. So this is 4.3 plus x, because this is x. This implies 9x equals to 4.3, this equals to 43 by 10. Therefore, x equals to 43 by 10 into 9. This is 43 by 90. Let's do 3. Given the number is 0.001 bar. So over here we have the repeating block of digits is 001 and we have 3 digits. We have we have 3 digits. So this is basically 0.001001001 and so on. Since we have 3 digits in the repeating block of digits, we multiply with 1000. 10 to the power 3 is 1000. So 1000 x will become if you multiply this with 1000, it becomes 1.001001 like this. Now this is nothing but 1 plus 0 0 1 0 0 1 like this. And the second term is x 1 plus x. This implies 9 9 9 x equals to 1. Therefore, x equals to 1 by 9 9 9. Okay. Uh, uh, what is 4? Problem number 4 says express 0.99999 in the form p by q. So, given that we are given, if the problem is express 0.9 like this in the form, that is, we have to convert this non-terminating recurring decimal into rational form. Uh, Rational form, obviously, where q not equals to 0. Okay, so we are given x equals to 0 point, basically this is 9 bar. We have the 9, the digit form 9 is repeating. So we have the repeating block of digit is 9 and we have single digit. This is 9, 9, 9 and so on. So we multiply with 10 and we get 10x equals to 9.999 and so on. This is equals to 9 plus 0.999 and so on. This is equals to 9 plus x. This implies 9x equals to 9. Therefore, x equals to 9 by 9. Quite surprisingly, it is 9 by 9 equals to 1. That is why the question says, are you surprised by your answer? With your teacher and classmates discuss why the answer makes sense. Why 1, why ultimately we got, ultimately we got the rational form as 9 by 9, which is basically 1. And but so it means that one has the decimal 1 is equal to 0.99999. So this is a little, definitely a bit of surprising. You can discuss with your teacher. As of now, I don't have the answer why this will make any sense or not. As the question says, are you surprised by your answer? With your teacher and classmates discuss why the answer makes sense. I have no knowledge why this will make sense or not. I will look into this question later on and come up with an answer if I can. Okay, so what is 5? What can the maximum number of digits be in the repeating block of digits in the decimal expansion of 1 by 17? So what can we have already discussed that a number, a rational number of the form 1 by n, where n is an integer and n not equals to 0, the 1 by n will have non-terminating recurring decimal expansion. If it is, I mean, it may not have, for all n, 1 by n may not 1 by n may not have a non-terminating recurring decimal like 1 by 2. No, 1 by 2 is 0.5. So if 1 by n for some integer n, if 1 by n has a non-terminating recurring decimal expansion, then then uh, the maximum then the maximum number of digits then the maximum number of digits in the repeating block of digits 1 by n will have non-terminating if it's better to write if 1 by n has if 1 by n for n is an integer and not equals to 0, if 1 by n has non-terminating recurring decimal expansion, then the maximum number of digits in the repeating block of digits in the decimal expansion in the decimal expansion will be n minus 1. It is always less than n. We have discussed earlier when we were doing in the very beginning, when we were doing the long division method, finding the decimal expansion of 1 by 7, 1 by 7, this thing, 1 by 7 or 1 by 3, we saw that we discussed that the number of digits in the repeating block of digits in the decimal expansion will always be less than the divisor. So the maximum it could be 1 less than the divisor. So that is the reason over here the answer is we are saying that if 1 by n has non-terminating recurring decimal expansion, then the maximum number of digits in the repeating block of digits in the decimal expansion will be n minus 1. So answer for 5 1 by 17 will have maximum 16 digits in the repeating block of digits of the decimal expansion. So the repeating block of digits in the decimal expansion of 1 by 17 will have maximum 16 digits, which is 17 minus 1, 16 digits. What does problem 6 says? Look at several examples of rational numbers in the form p by q, where p and q are integers with no common factors other than 1 and having terminating decimal representations. Can you guess what property q must have? It is saying that if we have, if it is saying to consider some rational numbers p by q where p and q have no common factors, that is, p and q are co-prime. When p and q do not have any common factors other than 1, they are called co-primes. So let's consider some co-primes like say 2 by 3. This is a co-prime where the number should have a terminating decimal. 2 by 3 doesn't have a terminating terminating decimal. 2 by 3 is 0.66666. No, this is not an example. You must have a terminating decimal, but Terminating decimal. Okay. So terminating decimal. Okay. So how about just consider a terminating decimal, any random terminating decimal, let's say one, uh, any, say three. Look at several examples of rational numbers in the form p by q, where p and q are integers with no common factors other than 1 and having terminating decimal representation. Terminating decimal representation. Uh, hmm. So any terminating decimal representation, decimal expansion will have some fixed number of digits after the decimal point. So this is definitely a rational number with a terminating decimal expansion, and this can be obviously written as 123 by 1000. Now, so where p is 123 and q is 1000, and definitely p and q are uh, co-prime. That is, we do not have any common factor between 123 and 1000. So what do we see? What property, what is so special about the q? Over here q is 1000. Okay, let's take another example. Let's say uh, terminating. Hmm. Terminating. Hmm. Hmm. Uh, let's see another example, maybe okay, 4.5, 4 by 5. This is 0.8. 0.8 is a terminating, have a terminating decimal expansion, which is 4.5, 4 by 5. So we have 5, and over here 4 by 5. Okay. So let's consider some more examples like uh, mm, mm, 6, 5 by 6, 6. Can we consider 6 as q and form a rational number p by q where we'll have terminating decimal? We'll have terminating decimal. Uh, we'll have terminating decimal. Mm, can we have any number like p by 6 will have some terminating decimal? Mm, what about terminating decimal 1, 2? If you have considered this, what will be p? P is P 7.2. P 7.2. No, P must be an integer. P must be an integer, so this will not work. 4 by 5. Mm, 4. Mm, the okay. The thing is, any terminating decimal will be any terminating decimal will be of the form. Uh, it will have some finite number of digits after the decimal. Hmm. Look at several examples of rational numbers in the form p by q, where p and q are no common factors. Okay, so what can be other rational numbers? Hmm. we can have also 7 by 2. This is 3.5. This is also having terminating decimal, and 7 by 2 do not have any common factor. What else we can have? What else we can have? Mm, 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 mm. Uh, can we have 3? No, we cannot have 3 in the as Q. So it turns out to be the fact that Q has, I'm not sure at this point, but Q seems to have 2 and 5 as factors. So any rational number which has a terminating decimal expansion in the form P by Q, where P and Q are co-prime, for that Q, whatever the number integer is, it must have, it is having 2 and 5, it is having 2 and 2, not 2 and 5, 2 or 5 or both as a factor. Because what is the reason? Any any terminating decimal will be of the form, let's say it will be of the form ABC dot XYZ. Let's say it has 3 digits after the decimal point and some digits before the decimal point. So the number is, if the number is ABC dot XYZ, this is basically ABC XYZ divided by 1000. Now 1000. So any terminating decimal, we can always convert it into P by Q form by removing the decimal point and dividing that number by some power of 10, and the power will be the number of digits after the decimal point. So we are having 1000. We are having 1000 in the denominator, like in, but it also says it only asks to consider those rational numbers where P and Q will be co-prime. There will be no factors, common factor between P and Q. So the common factor 1000, I mean any power of 10, the only two factors are 2 and 5. Any 2 and 5, okay. So we can consider P as something which do not have the factors 2 and 5. I don't know. I'm not able to properly answer this question. Somehow it feels that the Q will be of the form 10 to the power something. So Q will have as a factor either 2 or 5 or both. Okay, I will leave it here. 7. What does 7 says? 7 says write 3 numbers whose decimal expansions are non-terminating, non-recurring. Write 3 numbers whose decimal expansions are non-terminating, non-recurring. Meaning it is asking to write 3 numbers whose decimal expansion is non-terminating, non-recurring means it is an irrational number. That is 3 irrational numbers. It is basically asking to write 3 numbers whose decimal expansion is non-terminating and as well as non-recurring, which means after a decimal point we will have infinite number of digits and there will be no repeating pattern. There will be no repeating string of repeating block of digits. So we can arbitrarily write such numbers. So we can say, let's say 0.10110 10001, no pattern. This could be 1 or 2.18293674112 any. Let's say 1.99023567320176, any random you can write. Okay, what is 8? Find 3 different irrational numbers between the rational numbers 5 by 7 and 9 by 11. 5 by 7 and 9 by 11. Okay, write 3 irrational numbers between 5 by 7 and 9 by I think we have already computed the decimal expansion of 5 by 7 and 9 by 11 before. Let's see, 5 by 7 we did, 5 by 7 was 713, this thing, 713285, 7138, 713285. Seven one three two eight five and 9 by 11. Did we do 9 by 11? 9 by 11. What is 9 by 11? In the example, is 9 by 11? 14 by 11? No. 9 by 11. 9 by 11, 9 by 11, no. So we have to find what is the decimal expansion of 9 by 11. So let's quickly do that. 0.888 0 1. Oh, it just started repeating. 88 1. Okay, so this will be 9 by 11 will be 8181 like this. This is 0.81 like this. Okay, so we have 5 by 7 as 0.713285 baht and 9 by 11 as 0.81 baht. So we can consider any number where the decimal part, where the decimal, we have to find irrational numbers. What does irrational number means? We will have infinite number of digits but with no repeating block of digits. So three rational numbers. So first irrational number uh, lying between 5 by 7 and 9 by 11 could be we can take any number, we can start with 7 and immediately we can write here 2, and so 7 2 is definitely greater than 0.71 but less than 0.81. So now we can arbitrarily add any random digits 1 1 2 3 4 with no pattern like this. This will this will be 1. Second could be uh, second could be you can take 0.8 but do not take 1 but 0. Let's say 0. Now you can take any 9 2 3 1 0 0 4 5 any random with no pattern like this. third third could be again, let's say I start with 0 7 1 let's say 3 2 but instead of 8 I will take 7 and now I will add a random digits like this. I hope you understood the idea. That was 8. What is 9? Okay. Classify the following numbers as rational or irrational. Uh, root over 23. Root over 23, we already we have already discussed in lecture 2, I guess, that for any positive integer, that is for any natural number n, root over n is always an irrational number until and unless n is a perfect square. If n is not a perfect square, then for any natural number n, root over n is an irrational number. So definitely 23 is not a perfect square. It is not a square of any other natural number. So it is irrational. Irrational. Root over 2225 is definitely 15 square. So this is 15. This is 15 by 1. So this is rational. Okay. Now 0.3, we know that any decimal expansion having any terminating decimal expansion is always a rational number. So this can always be written as 1 2 3 4. So this is rational. This is rational. 7.47, 8, 4, 7 and 8, then dot dot dot, meaning it is a non-terminating decimal. Do you see any pattern over here? 4 7 8 4 7 8. Yes, we can see a pattern over here. So we can write it as 7.478 bar. Since we see, so this is a non-repeating recurring decimal expansion and definitely it will be rational. Since all rational numbers either have a terminating decimal or a non-terminating recurring decimal. In this given number, we see the decimal decimal expansion is definitely non-terminating, but it has a pattern. The block of digits over here, the repeating block of digits is 478. So hence it is a rational number. The last one, we are given 1.101 0 0 0 1 1 0 1 0 0 1 0 0 1 0 0 0. Definitely it is irrational because it is the decimal expansion is non-terminating as well as non-recurring. We do not see any pattern, any repeating block of digits in the decimal expansion, and also it is non-terminating. Hence, it is non-terminating, non-recurring. Therefore, it is an irrational number. With this, we have completed the exercise 1.3. 1.3, and I hope you learned something from this video. And if you learned something, then please again support me by subscribing to my channel, like this video, and share with your friends. And also please stay tuned for my future videos, as I will be studying the NCERT textbooks thoroughly, all the chapters. Along with it, I will do the exercise problems. And as I said before, that after I complete a chapter, I will also do the NCERT exemplar problems from that chapter. That will be really interesting and fun and challenging, because NCERT example problems are really test the fundamental concepts of the chapter. It is a must for doing well in the board examination. Now, okay, let me see if I can bring the answers of the exercise problems to check whether I did it correct or not. 9 textbook answers, exercise 1.3. So we are doing exercise 1.3, right? We are doing exercise 1.3. Okay. So here is my solution, and here are the answers. Let's see. Okay, let's start from the end. For the 9, for 9, last one was, it says what? 1 and 5 irrational. Okay, so this is 1, this is 1, this is 2, this is 3, this is 4, this is 5. It says that 1 and 5 are irrational. So 5 is irrational and 1 is irrational, and the rest are rational. Okay, okay, fine. 8, okay, it gave some example. 3 irrational numbers between 5 by 7 and 9 by 11, and so it has 808008. So mine was 80923, something like that, and 7507 75. Yeah, that could also be another one. 75. Anyway, this is not a problem. Let's see number 7. 7, write three numbers whose decimal expansion is non-terminating, non-recurring. Okay, so I gave this thing. Okay, this will not matter. Mine is also right. The answer is also right. 6, it says the prime factorization of Q has only powers of 2 or powers of 5 or both. Okay, I guess pretty much that's what I said for 6. Okay, so important to note that for a For a rational number of the form p by q, if p and q do not have a common factor, then q must have prime factorization. Prime factorization of q will only have factors powers of 2 and 5. Okay, so you can please note it down. Problem number 5, what it says, problem number 5, what 0.588, what was the question? Problem number 5, what can the maximum number of digits be in the repeating block of digits in the decimal expansion of 1 by 17? Oh, perform the division to check your answer. I did not I have not performed the division actually. So the division is this this thing, and how many digits it have? 0, 5, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So you see, for problem number 5, I have not done the actual division 1 by 17. So basically, 1 by 17 on 1 by 17 will be 0.00588 2 3 5 2 9 4 1 1 7 6 4 7. So this will be the decimal expansion of 1 by 17, and you can see that the repeating block of digits has 16 digits. That's what I said, that it will have maximum 16 digits. Okay, so 4, what was 4? 4 is says, okay, so or x equals to 1. So x equals to 1. We are getting x equals to 1, but it is a bit surprising. How come? Because 0.999999 doesn't really seem to be exactly same as 1. But when we converted this given number in the given decimal expansion to the p by q form, we are getting that the p by q form is 1 by 1. Okay, so for 3, 1, what we are getting? 1, we are getting 2 by 3. So 2 by 3, okay. And for 2, we are getting 43 by 90. Okay, 43 by 90. And for 3, we are getting 1 by 999. Okay, fine. It's right. For question number 2, okay. This I was not really sure whether I did it correct or not, but let's check it out. 2 by 7 is 0.285714. Mine is 0.2855714. Okay, 3 by 7 is 428571. Okay, 3 by 7 is right. 4 by 7 is 0.571428. Okay, fine. 5 by 7 is 713. Oh, I did wrong. 5 by 7. 5 by 7, I did it wrong. 5 by 7, I did it wrong. Okay, I will do it once again. 5 by 7, mine was wrong. Okay, I did the wrong. It might be I have done a mistake in the simple multiplication. So what it will be? It will be 7 5 35 25 28 40 42 10 14 20 21 and 7. Is this 5 by 7? Yes, now it is right. Okay, 6 by 7 is 857142. Okay, the rest are fine. Let's question number 4. No, we did Acha, question number one. Question number one. So 0.36 terminating fine. 2 is 0.09 bar, which is non-terminating repeating. Oh, I forgot to write here. This is non-terminating repeating. Third one was this thing, non-terminating recurring. Third one was, what was third one? 11. Oh, I wrote non-terminating recurring. Okay, fine. Third one is 4.125 terminating. Okay, yeah. Third one is 4.125 terminating. Fine. Fourth one was what? 0.2307690. 0.23076. Non-terminating repeating, non-terminating recurring, but I did some mistake in the repeating block of digits. Repeating block of digits. Why in the answer it is given 230,769, but in my answer I am having a 0 after 9 in the repeating block of digits. I think this 0 shouldn't be there. I did a mistake in long division method. This 0 won't be there. This 0 won't be there. So we won't have this 0. It will be like this, and so we won't have this 0. Okay. 4, 0.18, 0.18. Okay, non-terminating recurring, fine. And the sixth one, terminating 0.8225. Okay. Okay. So that was all for this video. Thanks for watching, and please stay tuned for my upcoming videos for completing this chapter. What we are left with, let me quickly check. For the chapter 1, we will next study the operations on real numbers, section 1.4. What do we have? Operations on real numbers. Exercise 1.4. Laws of exponents for real numbers. Okay, laws of exponents for real numbers. Exercise 1.5 and summary. So we will have another 2 lectures remaining for completing this chapter. One for the next lecture, lecture number 4, will be on operations on real numbers, which is section number 1.4, and then lecture number 5, the last lecture, we will study the laws of exponents for real numbers, which is section number 1.5, and then we will do exemplar problems. Okay, friends, I really hope that you are following my video and you are learning something. In case you are having any difficulty in understanding the concepts or in my way of teaching, or if you need anything more, anything specific to address, please let me know in the comment section. I will be glad and I will try my best to help you out. Okay, until the next video, take care and bye.